Hello, this is Matt 100 at Nassau Community College, and I'm Dr. Huntington. I'm going to demonstrate a linear programming modeling question just like the one that is in Unit 2 classwork packet, and it's on page 43. It's question 52 on washing machine production. First, I'm going to read the question. Washing machine production. A company manufactures two types of washers, top load and front load. The company can manufacture a maximum of 18 washers per day. Ooh, that sounds like a constraint to me. It makes a profit of $20 on top load machines and $25 on front load machines. No more than 5 front load machines can be manufactured due to the production restrictions. To meet consumer demand, the company must manufacture at least 2 front load machines and 2 top load machines per day. Okay, so let's list the constraints. I'm going to highlight them first. I see that here's one constraint. No more. Here's another one. At least 2 front load and 2 top load. Okay, and then the objective function I'll highlight in orange. So it looks like we're going to probably maximize, there we go, the profit. Alright, so let me list the constraints. So we'll say let x equal the top loaders, so the number of top load machines, and let y be the number of front load machines. Now that we have these variables defined, we can write the constraints. So for the first one, a maximum of 18 washers per day. So that sounds like the top load plus the front load machines has to be less than or equal to 18. Next, no more than 5 front load machines. So front load is y, so it's got to be less than or equal to 5. And then to meet consumer demand, the company must manufacture at least 2 front load machines and 2 top load machines. Okay, so it sounds like x has to be greater than or equal to the front load. Okay, 2 top load machines. So that's 2. They're both 2 actually, so looks like that. And so combining these two, if we notice, we can create a compound inequality. So that would be the same as saying 2 less than or equal to y is less than or equal to 5. Okay, so you can write both of them if you want, or just one compound one. So these are our constraints. And now next we're going to graph those. Part B asks us to determine the objective function. So this is the equation that we want to, or a function that we want to maximize or minimize. In this case, it's the profit equation. So we'll say that P equals $20 times the number of top load machines plus $25 times the number of front load machines. Next, we're asked to graph this set of constraints. So I'll create quadrant 1 here, and we have x and y. Now, in order to graph this one, I'm going to solve for y. Then I'll have slope-intercept form. So it looks like y is less than or equal to negative x plus 18. Then the other ones are pretty straightforward. So that means in order to graph this one, I'll graph it in red so I can use those colors that are over there. I'm going to start at 18 on the y-axis, and then I'm going to go down 1 over 1, down 1 over 1. Why? Because the slope of this boundary line is equal to negative 1. All right, so our m is equal to negative 1 and our b is 18. Now you have to decide, do you shade on top of the line or on bottom? Okay, you can do a test point if you like, or you can use the fact that it's all y's less than or equal to, since y is isolated. It's up to you. I'll do the test point. So I'm going to test 0, 0. So is 0 less than or equal to negative 0 plus 18? Yes. So that means we're going to shade the side, the half plane, that includes the 0, 0. So we're going to shade this way. Next, we're going to graph all y's greater than or equal to 2. So there's y equal to 2. And all things greater than or equal to are in that direction. And then all y's less than 5. That's going to be over here. Everything less than is in this direction. And then all x's greater than 2. So x equal to 2 is there. Everything greater than 2 is in that direction. So it looks like our feasible region is going to be this region here. And then our next goal will be to identify the vertices of that region. So we can use the fundamental principle of linear programming, which states that the maximum or minimum values of the objective function are going to occur at one of the vertices. So it could be at this vertex, this vertex, this vertex, or this vertex. Okay, here I've used Desmos to help me create a neater graph, and we have to determine the vertices. So let's start with the easiest ones first. Right here, this vertex is going to be x equal to 2. How do we know that? Right here. And y equal to 2. Okay, now over here, this one is going to be x equal to 2, and y equal, because of this one, and then y equal to 5 because of that one. Now we're going to have to use the line. I'll write it in slope-intercept form. Y equals negative x plus 18. Or actually, I can see it will be easier to use just the standard form of that line. X plus y is equal to 18. And that will help us to find these two vertices. Well, how? With this one, I know that the y is equal to 5, and I have to figure out the x. And then here I know that the y is equal to 2, and I have to figure out the x. Well, how do we figure out that x? Well, we know that x plus 5 equals 18 from this. Okay, so you subtract 5 on both sides, and you get that x equals 13. Same thing over here. We have x plus 2 equals 18. You minus 2 on both sides, so you get x equals 16. So now I've found all of those vertices. I'll highlight them. There's this point, and this point, and this point. Okay, and those represent these vertices. In part E and F, we're going to they're connected, so we're going to create a chart. So part E says how many washing machines of each type should be made to maximize profit. So we're going to look at all of the vertices and use the objective function. So I like to go through and write it all first. Right, so it's 20 times the x coordinate plus 25 times the y coordinate. That's going to equal the profit, and we're trying to maximize our profit. Okay, so now I'm going to fill in the x values and the y values. That one is 2 and 2, then 2 and 5, then 13 and 5, and 16 and 2. Okay, the first row here. So it's going to be 40 plus 50 is 90. That's $90. Then second one is 40 plus 125. So it's going to be 155. I'm just checking in my head. 125 and 40. No, that's 65. See? I had to check it a second way. 40 and 20. Yes. And then next we have, I'm going to do 260, 520. Oh, no. So 2 times 13 is 26. And then times 10 is 260. 260 plus 125, right? So that's 385. And then next we have 20 times 16. So that's going to be 2 times 16, which is 32, times 10 is 320. Right, so we've got 320 plus 50 is 370. So which one yields the maximum profit? Looks like this one is our maximum profit, and here's the values. So this is our max profit. And what are we going to be making? 13 top loaders. And 5 front loaders. How did I know that? Because the X represented the top loaders and the Y represented the front loaders. And here's the final answer. For parts, this one is part F, and this one was part E. To summarize what we need to do for a linear programming modeling problem, first you're going to determine all necessary constraints, then you're going to determine the objective function, that's the function you're trying to maximize or minimize. And then third, you're going to graph the constraints and determine the feasible region. Okay, and that's by the shading. And then determine the vertices of the feasible region. Sometimes it'll be obvious to you, but sometimes you might need to use techniques that you've learned from the solving systems section, where you can solve by substitution or the addition/elimination method, or you can use a graphing calculator or device. Okay, and then the last thing is to determine the value of the objective function at each vertex. And you're going to then look for either the maximum or minimum value, whatever you're looking for. And then the coordinates are the vertices. The coordinates are the ones that are also part of the solution that create that maximum or minimum value. Great job.